Our society today is generating massive amounts of data, recording digital transactions, social media posts, and all sorts of information from sensors and devices spread everywhere. Handling all of this big data is one of the main things driving the continued development of computers. In order to handle that large amount of data, though, we need a way to store it. We need to be able to store not just a few variables, but dozens, or hundreds, or thousands. If you think about how we've handled variables so far, where we declare each one separately, it's quickly apparent that this approach will not scale up to thousands of variables. It's not practical to come up with thousands of names, or write thousands of individual declarations. Now fortunately, there's a solution for handling however much data you have. In fact, there's more than one solution. We're going to talk in this lesson and the next lesson about two methods for storing data: arrays and vectors. So, this lecture is part one of a two-part lesson. We're going to talk about arrays here, which reflect the historical roots of C programming. Arrays were a part of C. However, if you stop with arrays, you'll miss one of the big improvements of C++, and that's vectors. Vectors will be the topic of our next lesson, but to understand how vectors work, you really need to first understand arrays. Let's say that we want to store one variable. We declare a variable, and that creates a box with that variable name that's stored in memory. If we want a second, we declare a second variable, and that gets a new box in memory. Now, what if we wanted to allocate lots of variables, say 20 of them? It'd be pretty painful to declare 20 different variables. Instead, wouldn't it be easier to say, I want a set of 20 variables? That's what an array will give us. An array is a collection of some number of variables. All the variables will have the same type, and all will be referred to using the same name, with a separate way of identifying each individual variable. Let's walk through some code to see how arrays work. To declare an array of variables, we start with the type of the variable we want. In this case, it's an integer. Remember that all the variables in an array have to be of the same type. We then have the name of the array, which is test_array. Obviously, it wouldn't be practical to name all the variables with different names, so we refer to the entire array, the entire group, by one name. Then, after the array name, we have a pair of square brackets. These let us specify the size of the array, the number of elements in the array itself. In this case, we're setting up an array of size 20. If you know about vectors and matrices in mathematics, they're described using square brackets. Well, an array is kind of similar to a vector or matrix in math, so it makes sense that we use square brackets here also. Now, what happens in memory is that these 20 boxes are all set aside in one big block. One block right after another. After the array has been declared, that is, after that long stretch of boxes has been set aside in memory, we can refer to each individual box as a separate variable. To do this, we'll again use the square brackets, each one containing a number, after the array name. So the first such box will be number 0, the second one number 1, and so on. We refer to a box by the array name, and then in square brackets the box number. Now, this might seem a little weird. Why are we starting the numbering with 0? The short answer is because it's a little more efficient. Starting the numbering at 0 might take some getting used to at first, but most people adapt to it after a little experience. After all, in Europe, unlike in the US, many buildings number the floors starting from 0. You might think of the ground floor as being the 0th floor. Some people joke that you can always tell who's a computer scientist. That's the person who starts counting from 0. Or says something like, you have 3 choices. Would you like number 0, number 1, or number 2? Anyway, in memory, the box numbers do start with 0. And to access any of the boxes of memory in our code, we just use the array name followed by square brackets containing the number of the box that we want. In the code example here, we're assigning values of 10, 20, and 25 to the first 3 boxes in the array. Notice that we can assign values to them, and we can refer to the values inside them just like with other variables. Now, I need to say a little bit about the terminology we use to refer to arrays. Generally, we refer to the whole array as the variable. That is, even though the array is made up of lots of different boxes, which you could think of as lots of different individual variables, we refer to the entire array as the variable. We'll generally be able to refer to the entire array, the entire collection of boxes, as one thing, and so it makes sense to call it a variable. We call the individual boxes the elements of the array. The elements are the component variables of the overall array variable. The number identifying an element is called the index. To refer to an element of the array, the common phrase used is sub, and then the index number. Sub can be thought of as short for subscript, and this comes from math, where we often use subscripts to refer to a set of items numbered in sequence. So, if we have an array variable a, we would refer to the first element as a sub 0, the next element as a sub 1, and so on. One of the things that makes using arrays feasible is that we can use a variable to represent the individual index. Suppose we create a small array named A with 5 elements, and say we assign the values 10, 20, 30, 40, 50 to the 5 elements. Then we create an integer index I that we initialize to 3, and we print out A sub I. What do you think the output here is? This prints out the value that was assigned to A sub 3, which was 40. When we access a single element of the array by listing the array name and then putting the particular element index in square brackets, we say that we're indexing into the array. That is, we're accessing array elements using the index of an element. The ability to index into an array by using a variable that contains the index gives us the ability to easily address all the elements of the array by looping through it. For example, we can set all of the elements to initial values. Say we were playing a 4-person game, and we wanted people to have the same amount of money to start the game, something like $200. We would first create an array. We could write int player underscore money, square bracket, 4, square bracket. This would declare an array named player money with 4 elements. Then we would loop over all of the indices. For this case, we can use a for loop to iterate over the values from 0 through 3. And we use I to keep track of the index. Within that loop, we could then set player underscore money sub I to 200, indicating that that player has $200. Since we loop over all 4 indices, we've initialized all 4 elements. Now, besides initializing, we can loop over the elements to process them. Let's see how that might work. Imagine that we want to read in a series of daily temperatures, and we want to report the average, and then list all the days that have a temperature greater than the average. We'll develop this program piece by piece. We're going to need 3 parts to this program, so our pseudocode will be pretty short, just 3 lines. First, we'll need to read in all of the temperature data. Since we don't know how many temperatures we'll have, we won't know the size of the array ahead of time. We'll have to pick a size that we think is plenty large. We'll also have to pick a sentinel value to let the program know when we're done entering data. In this case, that would be some temperature that no one would ever enter. When we read in temperatures, we can keep track of a count and a sum. Then we use the count and the sum to compute an average. Once we've computed the average, we can go through the temperatures again and print out those that were larger than the average. That pseudocode becomes comments. And now, let's see what this will look like as we fill in the details. Here's what the code looks like for the first part, reading in the temperature data. We begin by declaring an array of integers called temps. This array will hold the temperatures that we read in from the user. I've made an array of size 1000, since I'll assume that the user won't enter more than 1000 temperatures. When choosing an array size, you want to pick one guaranteed to be big enough to hold all of your data. But you don't want to choose a size unnecessarily too large. The bigger the array, the more memory is taken up. If you have arrays with many millions of elements, you can actually exceed the memory in your computer. We then set up some variables that we'll use in our program. Count temps will be the number of valid temperatures we've read in. Current temp will be used to hold the current temperature that we read in. And total will hold the combined sum of all temperatures. We'll use that to calculate the average later. Next, we prompt the user to enter a temperature, which we read into the variable current temp. Presumably, there will be at least one temperature, so we don't prompt the user for a sentinel value the first time. We then have a while loop that will repeat until the user does enter a sentinel value, telling us it's time to stop. Now, since we're recording temperatures on Earth, we won't have temperatures like 200, so numbers 200 or greater work well as a sentinel. Now, each time through the loop, we'll update several variables. If we're in the loop, then we had a valid temperature, current temp. So we set the next element of the array, temps, to this current temperature. Notice that the array is indexed by the variable countTemps. CountTemps is initialized to 0, and so the first temperature we have will go into the first array element, temps sub 0. After storing the temperature there, we add the temperature to the running total, and we increment countTemps. So, countTemps will hold the number of valid temperatures read so far. The elements of temp that will contain valid temperatures are the elements 0 through countTemps minus 1. Finally, still in the loop, we need to read in the next temperature, prompting the user. Notice that we instruct the user to enter a sentinel value when finished. So, at this point, we have a loop that will read in all of our temperature values into an array, keeping track of the total number of temperatures and the sum as well. The next segment of the program is just specifying what to calculate. We calculate the average by dividing the total sum of temperatures by the count of temperatures. Notice that we need to cast either the sum or the count to a float in order to get a floating point output. Finally, we output the average. Our last section of code should go through our array and print out the temperatures that were greater than the average. We begin by setting up a for loop with initialization of the variable, the condition, and the variable update. Notice that we declare a new variable I that will iterate through the array values. I is initialized to 0 and incremented by 1 on each iteration. The comparison ensures that this continues as long as I is less than countTemps. So, our loop is for int I gets 0, I is less than countTemps, and I++. I'll point out that this is a common format for looping through an array, where we know the size of the array. We set up a variable that is initialized to 0 and increments by 1 as long as it's less than the size of the array. So, if the size of the array is n items, our variable will end up taking on every value from 0 to n-1. Within the loop, we have a simple comparison. We check whether the element indexed by the current value of I is greater than the average, and we output it if it was. Notice that since I will take on every valid index of the array, this will let us examine every element of the array. And that's all. If we run this program, we can see that we're able to enter several temperature values, and then we get an average printed, along with the temperatures that were greater than that average. We can also initialize arrays directly. We've seen examples where we initialize a regular variable at the same time we declare it. It's a good idea to initialize everything so that you don't have memory sitting around with random values in it. There are actually a few ways that we can initialize arrays, and we'll take a quick look at all of them. The code you see here has an array declaration that we might use if we were keeping track of numbers of people on various teams in a competition. The array team members is declared to have size 5. To initialize it, we can specify the initial values that we want the elements to take as a series of 5 values separated by commas, all enclosed in curly braces. In this case, we initialize the array to have values 5, 6, 4, 5, 4. Sure enough, when we run this program, the for loop iterates through all the members, and the cout prints out values for each of the 5 elements in the order we specified them. Now, what do you think happens if we have an array of size 5, but we only initialize it with 2 values? Suppose we don't know the size of the other teams. Well, the first 2 elements of the array are initialized. When we print out the values of the first 5 elements, we see that the first 2 elements have the values 5 and 6, just like we specified. The last 3 elements all have the value 0. When you have array elements that aren't specified, they are often initialized to the value 0 by default. Again, it's usually a better idea to explicitly set any values that you want to be initialized, so that you know what's in the memory locations that you might access. Finally, we can declare an array without specifying the size if we initialize it with a set of values. In the code you see here, the array my_array is declared with an indeterminate size, where we don't specify anything in the square brackets. But we initialize it with a set of 5 values. So this implicitly defines the array to be of size 5. And we see that the values are all set correctly. On the other hand, if we just tried to declare an array with no size, we'd get a compiler error. Only when the array is initialized to something with a known size is it okay to leave the square brackets empty. Now, often data is more than just a single value. For example, if we have weather data, we might have a high temperature and a low temperature for each day, along with things like barometric pressure and amount of precipitation. We often want to keep track of multiple types of data at the same time, where the different data values are all tied together. For instance, we might want to keep track of both names and ages. The method that we'll focus on here is what are called parallel arrays. The idea of parallel arrays is simple. We create multiple arrays, each one holding a different type of data. And we tie these together by making sure that the same index in each array refers to the same item. So, if we have an array to store low temperature, and another to store high temperature, then element 20 in both arrays refers to the same day. We can get the low and high for that day just by using that index. Here's a really simple example. We have 3 parallel arrays, which are used to store a date. The 3 arrays will store a year, a month, and a day. We set the arrays to size 100, meaning we can store up to 100 different dates. So, we can assign a date by assigning the day, month, and year to the elements of the 3 arrays, assuming they have the same index. The example code shows assigning dates of January 1st, 2000 to element 0, and year 2007 to element 1. We can also have an array of arrays, or what we call multi-dimensional arrays. We can declare a 2D array by declaring with a variable name with 2 sets of brackets, each with a value inside. For example, imagine that we wanted to keep track of 5 people, each of which had 3 bank accounts, a checking account, a savings account, and a credit card account. So we would want an array 5 elements long, and each of those elements would be an array of length 3. So overall, we would want a 2-dimensional array, that is 5 by 3. We could declare this by a statement: double accounts, open bracket, 5, close bracket, open bracket, 3, close bracket. The name of the 2-dimensional array is accounts. To access some particular person's account, we would access an element. We do this by using the name of the account followed by 2 numbers, each in square brackets. For example, the 4th person's second account would be accounts sub 3 sub 1. And in this case, we assign a balance of $1,000 there. Remember that we start counting from 0, so the 3 indicates that it's the 4th person, and the 1 indicates that it's the second account. To set the value of the first person's third account to $50, we'd write accounts sub 0 sub 2 equals 50. Anytime we want to access an element in this array, we should specify 2 values, each in brackets. The first element should be a value from 0 through 4, the second element from 0 through 2. We can use nested loops to loop over all individuals, and then, for each one, over all accounts to see the results. And if we do that, whoa, we see some values that we set as intended, the $50 and the $1,000 that we just set, but there are a lot of other random values. Remember, we never initialized those. And so the information in them could be almost anything. But we can add one more set of nested loops at the beginning of our code, just after declaring the array, to go through all individuals and all accounts for each individual and initialize them to 0. Now, when we run the code, all the balances come out as expected. Using 2D arrays can obviously be useful if you have data that comes in on a 2D grid. For example, if we wanted to keep track of whether or not each square of a chessboard had a piece on it, we could declare a Boolean array that is 8 by 8 for the 8 rows and 8 columns of the board. But multi-dimensional arrays can also be useful when we have something that's easy to index in 2 different ways. For example, if we wanted to keep some number for each day of the year, we could create an array of integers that is 12 by 31. The first index would give the month, and the second index the day of the month. Obviously, there would be a few array elements that wouldn't get used, since not every month has 31 days. But that array would hold all the dates. And then, to find the number for a particular date, we could just access it by knowing the month and day. Regardless of whether we use one-dimensional or multi-dimensional arrays, there's one issue to be particularly careful of: array bounds. Let's look at this code example. We have an array named my_array of size 3. And we set the values of the 3 elements in the array to 10, 20, and 30. Now we have a loop that's designed to print out the values of the array. But instead of outputting 3 values, we make a mistake, and we have the loop try to print out 4 values instead. If you look at this for loop, the index I will take on the values 0, 1, 2, and 3, since the condition is less than 4. Now, 0, 1, and 2 should be fine, Those are part of the array, and we just set values for each one of them. But what happens when we try to print myArray sub3? When we run this, we might expect that we would encounter a compiler error, or some other error at the very beginning telling us that we're accessing an array element that's not there. Now, some compilers might be able to catch this and give a warning message, but this isn't what usually happens. If you're lucky, the program will just print out some value like 0 when the fourth element is printed. But what actually happens is not guaranteed. We could get almost any value printed out. In fact, we might find numerous lines output at once. The program might just crash completely. We have no guarantees what's going to happen. We call this an array out of bounds error. What's actually happening in the computer is this. The array, when it's declared, sets aside a block of memory with space for 3 elements. These 3 elements are all contiguous. They are 3 boxes located one right after the other in memory. When we declare an array, the array itself is considered to have the location of the first box in memory. To find the location of the elements, we just take the location of the array and go a number of boxes equal to the index. So for the first box, at index 0, we go 0 away from the start of the array. In other words, we're at the box at the same location as the array. And this is why indexing for an array starts at 0. Likewise, the element with index 1 is 1 box away. And the element with index 2 is 2 boxes away. When we try to access the element with index 3, we're just looking at the location in memory that's 3 boxes away from the start of the array. That's right after the last box that was set aside originally. We have no idea what's in this box of memory. It might not even exist. The array might have gone right up to the edge of the memory available on the computer. When we look there for a value, there's no telling what we'll find or what will happen in the computer. Maybe the program will crash, at least letting us know that there was a problem. But maybe it will carry along happily as if there's no issue, even though there's just some random unintended data being used. Unfortunately, there's no simple fix for this. Array out-of-bounds errors are one of the more common sources of bugs in C and C++ programming. This brings me to one of the biggest computer security flaws in recent years. In 2012, there was a software update installed on many computer servers that introduced a bug to a commonly used function on computer servers. The functionality was called Heartbeat, and it was a way of having one computer check that another computer was listening and active on the other end of a network connection. Basically, that it had a heartbeat, hence the name. The way the heartbeat function normally worked is that computer A would send a message to computer B, and then computer B should send a message back to A so that it was clear that B got and understood A's message. In other words, that it was alive, hence the name Heartbeat. Seems simple, right? Well, the specific way that this message system worked is that computer A would send a word or a line of text to B, along with how many characters were in that line of text. It needed to send the number of characters so that B would know how long the data being sent was supposed to be. Whatever was received by B would go into B's memory, basically an array of text characters. Then B would send back that many characters. Now, if everything was acting like it should, that's not a problem. Computer A would send a message, "I'm sending you the word hello," made of 5 characters. And computer B would receive that message, and it would reply, "Here are the 5 characters you sent, HELLO." And that way, A knows that B is connected and working correctly. Well, the problem here is that computer A could be acting maliciously, being run by an attacker who wanted to steal information from computer B. Instead of saying, "Hello is 5 characters," there was nothing preventing the malicious computer A from saying, "Hello is 50 characters." And the way the heartbeat code was written, computer B would happily return 50 characters of its memory. It would read past the end of the array, past the 5 characters of hello, and return whatever was in memory after that. Sometimes it might be useless random junk, but other times it would include sensitive information like usernames and passwords. This was not what was intended, and it all came down to a bug in the heartbeat code that let an array out of bounds error occur, the exact error we've been talking about. Since the name of the original program was Heartbeat, the bug became known as the Heartbleed exploit. And Heartbleed was in place for more than 2 years before it was discovered in 2014 by people who wanted to fix it. It was unknown how many computer systems were compromised and how much information was stolen by exploiting the Heartbleed bug. Some people think this was the worst security flaw ever to exist in any computer system. And it was all due to reading past the array bounds. So, be especially careful when using arrays that you try to consider whether you might possibly have an array out of bounds error, and if so, what you can do to avoid it. While you might not be writing sensitive server code used worldwide, you can still have errors that will cause your program to fail. The arrays we've been describing are the simplest and most efficient way we can store large amounts of data in memory. Some arrays are 1 million elements long. And we can access all the elements of arrays very efficiently, whether a single array or a multi-dimensional array. In short, understanding arrays is fundamental to a lot of programming. What's the old joke? Why did the programmer quit his job? Because he didn't get a raise. Arrays were part of the C language, and they have a very direct relationship to the way data is stored in the computer. That's why operations with arrays can be very efficient. So, even programmers using C++ will still make use of arrays when they want to truly maximize efficiency, or they want to control precisely how data is stored in memory. For beginners, arrays are still a quick and easy way to store data, especially when you know exactly how many elements you will have. In our next lecture, we'll use our knowledge of arrays to explore the advantages of vectors for handling data, including some built-in features that help prevent array out-of-bounds bugs like Heartbleed. See you then.